that maintained itself for nearly 100 years until Newton's physics and closer observations of stars discovered that the things weren't quite so simple. But maybe people here have discovered another clever way out of this conundrum. Is it? That's really weird. They can hear me, but they can't hear me online?
That's right, yeah.
Oh dear.
We had this also in the outreach event once. Do you remember what you have to press here?
There's a button that must be pressed.
Well, we have record and stream, so
Okay.
they can see the picture, but they cannot hear the sound.
All right, is the sound being recorded?
It's on. Just turning the next head mic on, maybe.
All right, get more than one mic going. Test 1, 2, 3. Is that working online now?
That's a good question. We don't know.
Right. Everybody who's online, wave at us. Alas, we can't see you.
Because there's no more buttons we can press here. These are just screens and
All
stuff,
right.
and it's all fine.
How many PhDs does it take to?
Yeah, that's a good question. Okay, let's.
We'll keep going.
Yeah.
With luck, it's being recorded anyway.
So this is audio.
Test 1, 2, 3.
It's just the audio in here.
Okay. Audience microphones? No, that's not what we want. Right. But it almost works. It's almost correct. Right. We will continue. Here's the thing. If you really, really want to believe that the Earth is moving, but you've got these stars that seem to look really close, that means that if the Earth were moving, you'd be able to see that the bright stars which are closer to you appear to move compared to the distant stars that are not close to you. There's a way to get around this conundrum, to have the stars really, really far away. Anybody come up with it? What if stars are not like the sun, but enormous, faint balls of gas, balls of whatever? This is, in fact, what Kepler believed, that the stars are very far away, but the Earth is moving, therefore the stars are not the same thing as suns. And we can tell that if they're that big and covering that much area, and you put all of the stars together, it's not nearly as bright as the moon, therefore they must be really dim. That was the line of argument. Wonderful scientific arguments based on actual measurements that no one could go around. I suspect the people in this room see the problem. The problem is the wave nature of light. If you've got a harbor with a gap and the sea is coming towards the harbor and waves are going through the gap, that's not what you see, a nice line of waves that suddenly stop. What you see are waves spreading out. And of course, anybody who's played with a ripple tank is familiar with this. The wave nature of light means that any wave going through the aperture, like the less than 1 inch hole in Galileo's telescope, will be spread out into what's called an airy circle. The disk of light you're seeing in the telescope is not the disk of the sun. It's simply an artifact of the size of your telescope. And if you've only ever used one telescope, because that's the only telescope that we have at the moment, there's no way you're going to know that. If you don't know that light is a wave, there's no way you're going to know that. Notice something else that's really nefarious about this. The width of the airy disk depends entirely on the geometry of the telescope, the aperture of the telescope. So if you have a fainter star, it will only be half as bright, but it will be spread out just as much. Now, the human eye cannot see all the way down to zero brightness. It only sees down to there, which means that to the human eye, a bright star will look bigger than a faint star. All of the things that the old model expected to see was being seen. They just weren't seeing what was really going on. Excellent observations leading to an obvious but wrong conclusion. In this photograph of a double star, you can see that the bright star is in fact bigger in the image. Anybody who's tried to work out a point spread function on CCD data, you know how that the spread is much bigger for a brighter star. It's just the way the optics works. Notice something else in this image of a double star. We know about double stars. Usually double star has got a primary and a secondary. Primary is a whole lot bigger magnitude, brighter than the secondary. Star A and star B are at the same distance from us. Just because the star is brighter doesn't mean it's closer. In fact, the first assumption of that argument, that stars are like the sun, is wrong. The sun is a star, but most stars are different from the sun. Of the 100 stars closest to planet Earth, 80 of them are so faint you cannot see them with the naked eye. There is no simple correlation between the brightness of the star and the distance because stars come in such an enormous range of brightness and sizes that it swamps the effect of being near or far, unless you know the kind of star you're looking at. Again, the kind of information that was completely unavailable at the time of Galileo. Galileo, in fact, argues that if you could find some tiny star next to some larger star and observe it over the course of a year, he would be vindicated. He still believed this in 1632. Was there a case that Galileo had seen a bright star next to a tiny star? Well, you know your Big Dipper or plow or whatever you call it. The star in the middle of the handle, it's not only an optical double, but in fact, when you look at the primary, it is itself a double star. We have in Galileo's notebooks that he was able to split that double star to see both parts of Mizar. And we know that he observed it over the course of a year. And of course, he saw no difference, because in fact, they are two stars of a very different brightness, one orbiting the other at the same distance. So even if he could measure to a really high precision, he's not going to see parallax. He didn't know any of that. But he did know that he didn't see the effect that he expected to see. So what did he do with this data? He never published it. He was a modern scientist, what can I say? I don't know if you know the story of Sidus Ludovicium. He didn't give that name. It was another aspiring astronomer who was trying to get money from King Ludwig that said, I've discovered a new planet and I'm naming it after you. So it carries the name to this day. This is an example of really good science being used to argue against the Copernican system when we now know heliocentrism probably is a better model. But at the time, the data didn't support it. A very different version of science going wrong, one that still boggles me, is Bode's law. Most of you probably know that Bode's law was actually not invented by Bode, but by Titius. But Bode was the first to publish it, and it's in a footnote. This is the footnote on page 635 of his book, which one of the books we have at the Vatican Library. It's wonderful. You can just go into the library and grab these things off the shelf. And the system works like this. If you take a body and you start as arbitrarily with 4, the second body you add plus 3, then plus 3, the difference between those two, and then double that, 16, and then double that plus 4. You get this mathematical progression of numbers generated by Bode compared to the number of AUs And you see, it actually matches pretty well. If you move the decimal point, you've got Mercury at 0.4 AU away, Venus at 0.7 AU away, the Earth by definition 1, Mars 0.52 instead of 0.6. Ceres was discovered because people saw this law and said, there's a gap at about 2.8 AU. There must be something there. They looked and they found Ceres. Jupiter seems to fit. Saturn seems to fit. And when Uranus was discovered, it also fit. It's an arbitrary formula, but it seems to work. There must be something fundamental going on so that when you're going to start looking for a planet beyond Uranus, you would expect to see it at 38.8 AU, and that's not where Neptune was. It works until it doesn't. On the other hand, Pluto is at 38.8, therefore it must be a planet. Where do you say it's coincidence, and where do you say that it's a law that almost works? Is there any significance to Boson? Well, part of it is simply the ordering of how much stuff you can have in a nebula and where you can put it together. There's another similar law you may be aware of. If you are sitting on the sun, looking out at the planets, the angle extended by the disk of Mercury is the same size as the angle of the disk of the Earth, is the same size as the angle of the disk of Saturn. Again, is this coincidence? Is this something fundamental? How come it doesn't work for anything else? It reminds you that going from observations and coincidence to trying to find laws isn't as easy as it looks, because let's face it, 4 really isn't the same thing as 3.9. 7 really isn't the same thing as 7.3. 16 really isn't the same thing as 15.2. In our desire to see a pattern, we tend to blur over the things that get in the way, the things that don't make the pattern work, until you're stuck with Neptune and you just have to throw up your hands and say, I guess it doesn't work. One of the great masters of science that was almost correct was Schiaparelli. I remind you, he's pronounced Schiaparelli because he's an Italian and the CH is hard. Schiaparelli was one of the great astronomers of the end of the 19th century. He's the first guy who looked at Mars and saw things that people hadn't quite seen before. Other astronomers, going back to Angelo Secchi in about 1860, had seen the dark markings on Mars, and Secchi, writing in Italian, calls them canali. And the dark Mars markings that Secchi found were real. But Schiaparelli, looking very carefully for a long time, also saw very thin lines, which he thought were also channels. When Percival Lowell and his telescope looked at Mars, he pretty much saw the same lines in the same place. And they were so narrow and so straight, and they seemed to connect Mars, which obviously has no clouds, with the pole caps. And when the pole cap shrinks, the dark areas grow. Lowell came up with the beautiful idea that these were in fact made by intelligent creatures to bring waters from the poles, to feed the countryside, to let crops grow. Notice the color that in this painting Mars is given. This is a painting of a globe made by a woman named Ingemar Brun about 1915, based on Percival Lowell. And she's using green to designate the dark regions. Next to it, of course, is a photograph from about the 1960s, about as good as you could do before digital cameras. You don't see the canals, But if you kind of squint, you could maybe see where the canals could be. And it's actually brown, but if you're expecting to see green, you're going to see green. We now know that there are no canals, that the poles are actually made out of carbon dioxide, not water, that when the poles sublimate, they increase the atmospheric pressure, which causes the winds to blow the red dust off of the darker rock to make the darker regions appear to be bigger. Percival Lowell's theory fit the data that he had at the time, and it satisfied his desire to see intelligent creatures on Mars, but neglected the fact that other possibilities were to be considered. Now, Schiaparelli did more than that. He observed Mercury and saw dark features on Mercury and kept seeing the same dark features every time he looked at Mercury. And every time he looked at Mercury, the dark features that he saw were aligned in exactly the same place. And so he writes, immediately and without any further calculations, the duration of the rotation of Mercury is equal to that of its revolution around the sun, which is to say 87.9693 days, good to 1 part in 1,000. And if you read science fiction as a kid like I did in the 1950s, it's full of stories of Mercury that one side is so hot that it's the hottest place in the world, in the solar system, but that far side in the permanent shadow is as cold as Pluto, even colder, because it never sees the sun. And there might be just this region around the daytime, nighttime side that might be habitable. And if you're a little bit older than me, you might remember when people finally bounced radar off of Mercury and discovered it wasn't so. The guy who did that, one of the guys who did that, Erwin Shapiro, was somebody I worked with, taught me planetary science. How did Schiaparelli get it so wrong? It's not that he didn't see features. He did see features. It's not that he mistook where the features were. The features were, in fact, exactly where you expect them to see. But Mercury is really hard to see because it's so close to the sun. And it turns out you can only see it about 3 times a year when the angle between the Earth, the sun, and Mercury is large enough that it's high above the horizon. And you would think, oh, the bigger spread is the easier time to see it. But it depends on the angle of the ecliptic. Even though in the picture to the left, Mercury is farther from the sun, it's still closer to our horizon because it's visible that way during the springtime here in the northern hemisphere. The opposite is true in the southern hemisphere, which means the best observations are done from the southern hemisphere. Schiaparelli didn't have that luxury. What Schiaparelli did do was to record when he made his observations. The curious thing is, the radar shows that Mercury does not keep the same face to the sun, but Mercury spins 3 times for every 2 orbits, which is to say it has a period of about 59 days. And if you look at the number of days between observations, Schiaparelli was stuck seeing Mercury in exactly the same orientation every time he looked. Who would have thought? Especially because we're used to the Earth, the Earth's moon always being pointed to the sun. You would expect Mercury being to the Earth. The same face. Try that again. You always see the moon. You always see the moon's one face pointing towards the Earth. You would expect that Mercury and the sun would have the same relationship. It turns out because of Mercury's elliptical orbit, the spin rate it would have if it was moving as fast as it is at perihelion turns out to be 59 days. And there's a complicated resonance between the size of the orbit, the spin of Mercury, mathematics, which is really elegant, but I won't go into here. The point is, if nothing else, you have to say that Occam's razor doesn't always work. The world was just a little more complicated in such a way as to fool Schiaparelli. Schiaparelli made one final calculation, which I just find astonishing, and that has to do with showers of meteors. Meteors, of course, occur in regular showers, but every period there are certain meteor showers that are especially powerful. So here we've got the map of the sky as given to us by H.A. Rey. I hope you guys know about the H.A. Rey book, The Stars. Great book. I still have the copy I got when I was 10 years old. Shows the constellations as little stick figures. You can always remember what the constellations are. Notice Leo the Lion off there to the left. If you take a picture of a meteor shower, as my friend Yuri Toth did, you notice that most of them come out of the part of the sky where Leo the Lion was. And these are called the Leonids for that reason. And the Leonids not only show up at the same part of the sky the same time every year, but every 33 years, they are especially strong, especially interesting. Good old Schiaparelli noticed that, and he says, I know what's going on. The Earth is plowing through a stream of dust that orbits the sun. The reason why you see these showers mostly in the early morning is because that's the side of the Earth that's plowing through the dust. The meteor shower is the dust hitting the Earth in such a time when Leo happens to be on the opposite side of where the dust is coming from. From knowing the angle of where the dust was and the 33-year period, he worked out the size of that stream, which I think is just astonishing celestial mechanics. He worked out the period, and from that the semi-major axis, and from the angle at which it was hitting, he could work out an eccentricity and therefore perihelion distance, and inclination, longitude, the node. And then he noticed that this exactly matched the orbital elements of Comet Tempel-Tuttle. Brilliant work. He shows not only that meteor showers come from a stream of dust that the Earth is moving through, but that this dust is related to a comet. Fantastic work. So why do I have him here among the almost correct? Because out of that he concludes that comets must be made out of the collection of streams of dust. After all, that's the way that gravity works, right? Gravity only pulls things in, which of course is exactly the opposite of what we know is happening now, because comets are full of gas, full of ice, which is causing the dust to go out rather than in. So close, almost correct. Now, I've been ragging on these other astronomers. I want to end with a somewhat longer story that involves my own research. I remember, 20 years ago, I'm reading the Harry Potter book. I think it was Goblet of Fire. And Harry's doing his astronomy homework. And Hermione is checking it over. And she goes, Harry, the moons of Jupiter are covered in ice, not mice. And I'm going, that's my thesis. That's what I did. I wrote my thesis in 1975 at MIT on the moons of Jupiter and how they're covered with ice and why they're covered with ice. Oh my gosh, I'm being quoted in Harry Potter. Of course, nobody remembers that I did that. Until about 1995, 96, Arizona Press decided to have an entire book of papers on Europa, and I was invited to be a co-author in the very first chapter. So proud of myself. The very first chapter was the history of the study of Europa. And yes, I had written a thesis about it in 1975. That's what I looked like in 1975. It was the 70s. speaking of almost correct, in the first version I turned in, I had a typo in the title. I had given them the title a year before and forgotten the title and typed up the wrong title. I had to go back and, we reproduced at least the title page. The idea that we'd worked out was that Europa is a collection of rock and ice. And our idea was that radioactive elements in the rock might be enough to melt the ice. Would it be? I did the computer models and a big stack of computer cards running on an IBM 360-65. It took me about a year and a half to get the program to compile and about 1 month to come up with the data, the results, and to write it up. What the thought was, you'd have an ice crust, a liquid ocean, and a rocky and eventually iron core. These were not my pictures because JPL had a better artist than me, so everybody remembers their version. So I put that in, write that all up. It turns out, incidentally, that I got the right answer, but I underestimated the heat flow out due to the convection of ice by about a factor of 10. And I underestimated the amount of heat generated inside the body because I didn't know about tidal heating, again, by a factor of 10. So I got the right answer for the wrong reasons rather than getting the wrong answer for the right reasons like other people did. We're right up in the chapter. And the way the chapter is reading is, Galileo discovers the moon, part 2, Guy Consolmagno makes these stupid models that turn out to be wrong, as if nothing happened in between. This is kind of the NASA syndrome that everything that is in the universe, they discovered first. They went to Jupiter as if they had discovered Jupiter. I knew that wasn't the case because I wrote these models in 1973 and 74. And we didn't even have spacecraft to Jupiter until 75. We didn't know that the spectra of Europa had the spectral lines of ice until 71, but the work that I was basing this on, which is to say my advisor's work, John Lewis, he had published about the icy moons of Jupiter in the 1960s. So that led me to the interesting question. In 1970, before there were spectra, before there were spacecraft, everybody knew that the moons of Jupiter were a mixture of rock and ice. And you could even estimate from the density, the density of the rock, the density of the ice. You can work out from the density of Europa how much of it is rock, how much of it is ice. Everybody knew that. How did they know that? What did they know from what they knew in 1970 that made everybody sure they were made of rock and ice? There were essentially 2 bits of information that was known. First of all, the albedo, the intrinsic brightness. A typical rock like the moon reflects maybe 12% of the light that hits it. Europa reflects 64% of the light. Europa is not made of even white rock. Europa is made of something pretty darn shiny. And there aren't that many things in space that are shiny like Europa, but certainly ice is one of them. The other thing we knew was the density, the mass divided by volume. And the density of even Europa was significantly lower than the density of the moon, but higher than the density of ice. So you could work out if, ice has a certain density and rock has a certain density, what the proportions were, which were numbers that I put into my computer program. So if you knew the density, and of course the other moons of Jupiter have even lower densities, which is to say they have even more ice. So if you knew the density and the albedo of the moons of Jupiter, you should have guessed that they were made out of water ice a long time ago. Well, to know the albedo, you have to know the relative reflectance, and you have to know how big the thing is. Because either it's really big and kind of dark or very small and shiny. If you know how big it is, then you know the relative reflectance. To know the density, you have to know how big it is, but you also have to know the mass. How do you find the mass of a moon? Its orbit tells you the mass of Jupiter, but it doesn't tell you the mass of the moon. This is Galileo dropping, heavy things and light things. These moons are the heavy or light thing going, the orbit is the same. whether they're heavy or light. The only way you could come up with the mass of the moon is if you could make measurements about how one moon is affecting the orbit of another moon. Really nasty calculations that I sure don't know how to make. You know, when was anybody ever going to be able to make those kind of calculations? Well, it turns out this guy did it in 1803. Laplace was like that. And he comes up with masses in terms of the mass of Jupiter, which you can measure from the orbits of the moon. And of course, big G. You have to know big G in order to know how many kilograms and stuff we're talking about. When was big G measured? And who did that measurement? Anybody here ever hear of a guy named Cavendish? 1795, big G was measured. So they had all of that information. They knew the masses. And in fact, when you take those numbers, the masses are good to about 10%, except for the mass of Callisto, which is off by about 25%, but still not bad. Next, how do you measure the size of these things? Because after all, they're pretty much dots in the telescope. But what you can do is see how one planet turns on and off, and how long it takes to go behind Jupiter, or what happens when they have mutual events and one is passing in front of the other. All of this is possible. Actually, what they did is they stared at the telescope for a really long time until they thought they were seeing disks, and then measured the disks. And the strange thing is, the numbers they came up with weren't bad. It's only a couple of pixels across, and yet they were able to come up with numbers that were good to about 10%. They quoted numbers to 1/100 of a percent because they didn't quite understand these things. But by the 1840s, they had the sizes, they had the brightnesses, they had the masses, they had everything they needed in order to say that the moons of Jupiter were made of ice. So, who was the first person to finally say it? We have at the Vatican Observatory this wonderful collection of old books, not only Bode, but also 19th century. And I pull out two here in particular, The Popular Astronomy by Simon Newcomb. Newcomb was sort of the Carl Sagan or the Neil Tyson of his day, an American popularizer, but a very good astronomer. He was also the model of Professor Moriarty in Sherlock Holmes. And some of the things that Professor Moriarty was said to have published are papers that Newcomb actually did publish. Newcomb was an enemy of a friend of Arthur Conan Doyle. Newcomb writes in his book, according to the best determinations, the diameters of the satellites range between that size, and he gets, which are the biggest and which are the smallest. The light of these satellites varies to an extent which is difficult to account for, except by supposing very violent changes going on in their surfaces. When he looks at the brightness of the moons of Jupiter, they vary by a factor of 2 or 3 from time to time in a totally unpredictable way. In fact, the best theory is that these are not balls, but pancake-shaped. And sometimes you're seeing them flat on, and sometimes you're seeing them edge on. And anybody here ever see the moons of Jupiter in a little telescope? Anybody here ever notice that their brightnesses change by a factor of 2? Not only he says this, every textbook up until about 1870 says this. What the heck was going on? Furthermore, he never talks about the densities. Indeed, in every textbook from the 19th century up until about 1890, you will find tables of the moons, usually named 1, 2, 3, 4, rather than with the names we use now. You'll get their masses, you'll get their radii, you'll get their brightnesses, maybe, and nobody ever calculates a density. They had the mass, they had the size, But the idea of asking the question, how dense is it, is not an idea that anybody thought to ask. Because in those days, astronomy was a mathematical system. Your job as an astronomer was to determine the orbits to one more decimal place and work out the orbital theory to one more term in the equation. You never ask the question, what is it? Somebody had taken a spectrum of the sun and somebody had taken a spectrum of Sirius, and they saw these lines that they didn't know how to interpret, and they said, that's curious, and never went any further. When Angelo Secchi, the same guy who saw the canals on Mars, when Angelo Secchi first takes spectra of stars, he is roundly criticized for using up valuable telescope time on a totally pointless exercise. There was one exception. This guy, A Handbook of Descriptive and Practical Astronomy by George Chambers. I have no idea who he was, except that he published in London in 1861. And there he has a table with the density compared to water, or density compared to the Earth. Density compared to water. Let me pull up those. There's the mass. His mass is pretty good. There's the diameter. His diameter is pretty good. There's the density of water. Io has a density of 1/10 the density of water. Europa, 2/10. Ganymede, 4/10. Callisto, 2/10. Can you think of anything in nature that has a density 1/10 the density of water? Even balsa wood is denser than that. He puts out these numbers and never asks himself, what the heck does this mean? They're just numbers that he's calculated. What's more, the number he has for the diameter isn't that bad. The number he has for the mass isn't that bad. But these numbers are totally wrong. What's worse is that when you take his mass and divide by his volume, you're not getting the numbers that he puts here. They're not even consistently wrong. I have no idea where he got those numbers from. But whatever it was, he didn't even do that freshman physics. Does this number make sense? Let me go back and see if I made a mistake. Totally bizarre. Finally, at Harvard in the 1870s, Pickering comes up with a new gizmo for measuring the brightness of, and he comes up now with a new albedo based, these are the densities, I'd say, diameters of the satellites. Oh, he's got two different people giving two different diameters, slightly different sizes, and comes up with a pretty good guess as to how bright. He's actually off by about a factor of 2. But in any event, he sees that the moons of Jupiter are pretty bright, much brighter than rock, and it had been thought by many astronomers that the light of the satellites of Jupiter was variable. This is not sustained by the present measurements. There's no evidence of variation in the brightness. Why is he seeing something different from what had been quoted for the last 100 years? How do you measure brightness in the 19th century? You turn your telescope to the thing you're measuring, and then you turn your telescope to a standard star. And you guess from all the different stars which one seems to be closest to the brightness. And actually, the human eye is pretty darn good at interpolating brightness and coming up with measurements that actually measure photometric measurements we do today. But Pickering had a cleverer idea. Because Jupiter is in the field of view, he took two polarizing pieces of calcite and would twist them until the brightness of Jupiter matched the brightness of Europa. So he had Jupiter blunked out while Europa he was looking at. And in this way, he measured the brightness over and over and over again and saw no variation. Can you see where the problem had been? If you're using your eye as the detector and you're looking at Europa, when Jupiter is in the field of view, whopping big, bright Jupiter, your eye is going to go shrink and Europa is going to look faint. But if you're looking at another time when Jupiter is not in the field of view, then your eye is going to open up and Europa is going to look bright. So finally, he has solved this problem. This was about 1877. It will be noted that the densities, he then comes up with a table of densities. I guess I skipped that slide. And 20 years later, he comes up with a table of densities, and he has densities not far from what we see today. I'm surprised that that slide got lost. So this is about 1990. You'll notice that the densities given in the columns are very small for solid bodies. The density of the moon is about 3.4. The densities that they're coming up with are around 1 to 1.2. Such figures necessarily imply that these bodies are either enveloped in clouds, which is not very likely, and he points out that the gravity is not enough to support an atmosphere, or else their density and brightness is what we would expect if they were composed of loose heaps of white sand. So close, and then he says they're made out of sand instead of ice. Why? Because if they weren't loose heaps of white sand, then how could they have that disk shape, that flattened disk? That flattened disk was necessary to explain the variation in brightness that he had shown doesn't exist anymore. And therefore he concludes that they're white sand. The answer only comes from Sir Harold Jeffreys, working here at the Institute for Astronomy in the 1920s, where, in passing, in a paper actually about Jupiter and Saturn and its composition, he looks and compares the densities and the brightness of the moons and just passes off, of course, they're similar to ice. Finally, somebody who gets it right, right? Well, not quite, because he's using these guys being ice to support his idea that Jupiter and Saturn are also balls of ice. Not appreciating the density that would be so much, the pressures inside Jupiter and Saturn that would be so much greater that their interior density would be much higher than if they were just made of, you'd think that, Jeffreys should have talked to a geophysicist. He was a geophysicist. So once again, people studying the moons of Jupiter get it wrong. Now, I claimed that this was going to be a story on me, so I'll talk about it. My thesis, The Icy Moons of Jupiter, at the very end in the appendix, talks about how the radiogenic heat sources, given the temperatures of the interiors and the silicate layers through which the water is percolating, the possibility exists of simple organic chemistry taking place, either with methane in the ices or carbon in the silicates. This is my thesis. I wrote this in 1975. The last sentence reads, "We stop short of postulating life in these mantles. We leave that to others more experienced than ourselves in such speculations." What do I mean here? It's a dig at that guy, Carl Sagan, who had been going around for years proposing life on Mars, life in the atmosphere of Jupiter, life in... And here I am finding a place where there actually might be life, and I'm saying, I'm not going to go there. I'm just not going to touch that. The very first paper I ever gave in public, 1975, was at a big conference on Jupiter. Mine was the last paper of the first night. The chair of the session was Carl Sagan. I go up to Carl Sagan and say, "Icy moons, icy crust. water underneath, rocky stuff, maybe carbon, life in the oceans. Isn't that cool? I'm thinking he loves life. He's going to be excited. And he looks at me and he goes, Guy, life depends on sunlight. There's no way that sunlight will ever reach these oceans. There's not going to be any life there. And I'm going, oh, hell. He's right. So I didn't mention that in my paper. I didn't mention that in what I discussed. I forgot the entire thing until a few years later, in the darkest parts of the ocean, we discovered life living off of the energy of volcanic plumes, not living off of sunlight. And by golly, somebody else comes out on a paper about the habitability of Europa. The second author, Steve Squires, is a graduate student of Carl Sagan's. The difference is, of course, I was doing science fiction. They actually went through the calculations. They actually did the science. So, yeah, they deserve the credit. They can be the people who proposed life on Europa. I am the first person to not propose life in Europa. So what's the moral of the story? Science makes mistakes. That's, incidentally, why science is a lousy basis for any religion. But science corrects its mistakes. You learn from your mistakes. But the last bit to remember is that sometimes the mistakes aren't in your data, but in your imagination. Remember that picture of an icy moon covered with crystalline spheres of ice, just like the crystalline spheres of the original Aristotelian version. Thank you very, very much. Happy to take questions.
Thank you very much for a
Right.
really great presentation. We have a few minutes for a few questions.
Sure.
Are there any questions?
Yeah.
You said that everything we knew about Galileo was wrong, but you couldn't go into it.
Mm-hmm.
Could you sum it up in like 1 minute?
This year is 2024. Okay. Galileo was born in 1564. Do you know anybody born in 1964? The age that they are now is the age that Galileo was 400 years ago. A little timeline. 2 years ago, Galileo publishes this fabulous book on the philosophy of science called The Assayer. Stuff we quote to this day. The Pope's censor writes a 22-paragraph stanza poem in praise of Galileo, saying we will be remembered because we lived at the same time as Galileo, which is true. Galileo's best buddy is the Pope. Things are going great. He's living off of a book that he published 14 years ago about the telescope on a theory that was proposed back in World War II. So it's not like Galileo's ideas were new or radical or the stuff of young guys, because he's 60 years old. Galileo doesn't get in trouble until 1642 when he's 68. 32. He's 60. And at that point, he has a book that talks about the Copernican system and arguments against it. And it's approved by all the censors, and it's out and it's selling well when the Pope is shocked to discover things in this book that he had already read earlier. And he puts together a special committee to try Galileo, and every time, you can read the trial, every time they come up with a problem in the book that they don't like, Galileo says, sorry about that, I'll fix it. And they say, not good enough, we have to find you guilty of something. And at the end of the trial, he said, so you're a heretic. And Galileo says, no, I'm not. I have a certificate from Cardinal Bellarmine saying I'm not a heretic. And you haven't shown any heresy in the book. So he is found guilty of vehement suspicion of heresy, which is a weird thing to be guilty of. He famously gets up and abjures all the heresies in his work, right? We all know about this. What he says is, anything and everything in my book that is contrary to the church, I reject. without ever specifying what those things might be. Nor do they ask him to specify that. And a year later, he's back home in Florence in his estate, house arrest. Yes, but have you been to the house? It's a really nice place. And he's in his 70s. You know, he's 72 by then. He's aged and blind. I'm 72, by the way. And he writes another book on, you know, how physics works and gets that published. So the question is, if Galileo was doing great until a certain year and then everything fell in, and 2 years later he's back to pretty much where he was, why did they have the trial? It is not science versus faith. That's not what's talked about in the discussion of the trial at all. And what was it about? Two big theories. One, the things he said about the contrary view, which were the view of the Pope, which were based on the fact that Galileo didn't have the physics. He didn't have the stuff. He put it in the mouth of somebody called Simplicio, who was supposed to be the noble, if simple, but honest and wonderful man, except that the Pope was Urban VIII, from which we get the name Urbane, hated being called a simpleton. And maybe he was just pissed off at Galileo. A lot of people were pissed off at Galileo. He was good at that. He was an Italian. You know, it comes with the territory. Maybe. If that was the case, then the Pope was using his power as a Pope over religion to get back at Galileo for personal reasons, when that was a big mistake. That was an abuse of power. The other argument that's been made is that the trial happens to occur exactly at the height of the 30 Years' War, when the Protestants in the north are beating the heck out of the Spanish-supported Catholics in the south. The Spanish say, hey, this is a war of religions. Pope, come to our aid. Except that nobody likes the Spanish, including the Italians, because they're too powerful. The French, who are Catholic, are supporting the Protestants in the north. The French had actually been the ones who had gotten Urban elected. He's being accused by the Spanish of being a secret Protestant. You know, if the Pope's a Protestant, don't ask me what bears do in the woods. Maybe the trial was a way to distract people from what was going on, because a year later, the tide of war changed in the other direction, and Galileo was able to go home. It's a coincidence, like the coincidence of Bode's Law. There's no actual documentary connection that you can make. It's a mystery. But if it was either of those things, it was the abuse of the church's religious authority to go after somebody for reasons that were not religious. So that's why I say it wasn't this big science faith thing, but it was still a mistake, a terrible mistake. Other questions? Yeah.
On this same topic, I didn't know this part of the story. It's very interesting.
Mm-hmm.
Was it well known at the time? Because it did take the church until, I think, 1992 to formally rehabilitate it and say, we went wrong. So,
Okay, here's what happens. The Copernicus book, in Italy itself and no place else, if you owned a copy of the book, you were instructed to cross out the line that says the Earth is going around the sun, and write in the margin, you can calculate by pretending the Earth goes around the sun. That's the only change you had to make. Owen Gingrich has gone through all the copies of Copernicus. In the copies that were in Italy, only half of them were changed. The copy that we have at the Vatican Observatory, which is the Vatican's copy, isn't changed. You know, these are Italian laws. They're treating this like they treat stop signs there. There are some people who get weirded out by this, but the Copernican book continues to be taught at least as a great way of making the calculations. By the 1750s, after the scientific arguments had been resolved, people could understand the size of the star and the telescope is not really the size of the star. They could understand that Newton's physics could explain these orbits much better than what had been before. At that point, the church says it's okay to teach the Copernican system, 1750. Galileo's book itself is still put on the restricted list because they don't want to admit they were wrong. And it doesn't come off until like 1810. What happens in 1993 is that the Pope, getting ready for the year 2000 and trying to, says the church should go through and admit the things it got wrong. One of the things it got wrong was putting Galileo on trial. We're going to formally apologize to Galileo for that. But, you know, we've been doing astronomy at the Vatican Observatory for a few hundred years at that point and had no trouble with Copernicanism. Why is it that everybody still thinks that? Because in the end of the 19th century, there was great political hay to be made at making Catholics look stupid. Especially in Germany, where the Catholics were one political party against Bismarck, and in America, where Catholic immigrants, people with vowels at the end of their name like Consolmagno, were getting into the country and ruining the place. So they put up quotas to keep them out. My grandpa got in early. Or in Italy, where the anti-church, anti-clerical government was looking for reasons to make the church look bad. So they kind of invented this myth. It's a 19th century myth.
Thank you, very interesting.
Yeah. That's why I'm up here doing this, you know. Not that we didn't get things wrong, but we didn't get that thing wrong.
Okay, final question.
Yeah.
You mentioned Schiaparelli.
Schiaparelli. Right.
That person only observed it every, whenever it was facing
Right.
here.
Whenever it was as far apart from the sun as visible from Earth.
Do you have any idea why that might have been? Could it have been that you removed those data points because they seem different?
Have you ever tried to find Mercury? It's really close to the sun. The only time you can see it in darkness is when it's that far from the sun. And that's essentially why he kept looking at the same time. It was the easiest time to see it. What are the odds that Mercury would be spinning in just such a way that he would be fooled that way? Well, coincidences do happen.
Okay, so Br.Guy, he will be with us till Friday actually. He will also be at St. Edmunds and give you a
Right.
lecture tomorrow then. But you know, there is a schedule, so if you want to meet with him, please sign up. And that's thank you
Right.
again. Thank you very much.
Thanks, everybody. I do have some times tomorrow when I'm already scheduled, so I should probably, if I just email those to you,
Yes, I can.
you can make those corrections.
Yeah.
Okay, I'll do that.
Could you? I think they need an official document to be signed here. Just if you could sign, you know, maybe your name in this signature. You don't need to put in your email.
Right.
That's got something to say.
Sorry?
I just want to have a chat for it.
Yeah, sure. Yeah. I have to dash off, but
Right, today is the
19.
19th. Yeah. Perfect. Thank you very much. Yeah, I just
Wonderful talk.
Oh, thank you.
I wanted to mention something I find quite fun. So, a friend of mine, Alex Mustel, who is Mark White's PhD student at Company Dynamics, he published a little paper on the T-shaped mode law a while ago because he described it as a coincidence.
Okay.
It's almost barely a coincidence. So his result was if you randomly generate planetary systems, about 2/3 of them
We'll come up with something
will
like that.
obey some form of the T-shaped mode law.
Fabulous.
You know, you have to change the
I'd love to have that.
Yeah, I'll try and find it. You have to change the exponent or something. But yeah.
Right, but I mean, there's so many free parameters.
No, exactly. So yes, about 2/3 of random planetary
That's
systems.
brilliant.
you can fit into your movements. So yeah, so it's not it's barely a coincidence.
It
It's
is.
just you can do numerology.
It is, and yet you're really tempted. And I think the lesson for astronomers now is we see things that we're tempted to see are a pattern, but in fact are coincidence.
Well, do you think it'll be long before you have to update your lectures so that you included another model that's not antecedent?
I'm not going to touch that.
Very
I'm
good.
immediate reticence.
Well, that's I'm sorry, that is definitely religion.
Yeah.
So, given that aberration is 20 seconds, why wasn't discovered earlier? And the motion of the Earth.
and then
which,
Aberration.
oh, the aberration.
Aberration. Light aberration.
The aberration was actually seen in the 1700s. But why it took so long to be seen, I don't know the actual history behind it. That's a good question.
It was confused with parallax.
Yeah, it was confused with parallax originally. Parallax wasn't until the 18th century. But the aberration was seen. I think the difficulty is finding, basically everything's aberrated. So finding the fiducial against which you can measure it. That might have been the trouble. That's in the back of my head. I wouldn't say that was the case.
There's a big difference between aberration and parallax.
Yeah, absolutely.
It should have been discovered in the 16th century aberration. If Tycho Brahe really measured down to 10 arc second.
But again, I think you have to, what is the fiducial against which you measure it? And I don't think they thought to think that through, because they didn't expect to look for it. They didn't expect it, therefore they didn't look for it. They were only looking for the
Prejudice
parallax of
plays
distance.
an important role.
Absolutely.
But still is a big effect.
Yeah, and of course prejudice plays a huge role in, we see the things we expect to see in our day.
Absolutely.
We're all
That's
guilty
what
of
I
that.
teach my students.
Yep, exactly.
It's difficult to see the new thing.
Yeah. And
Yeah, it's transparent.
And it's not clear when you say, okay, I give up, the theory doesn't work, to say, if I just work a little bit more. And sometimes you need a little more work, and sometimes you have to give up. I mean, my case with the life in Europa, I gave up too early.
Tiny, like millimeter dips.
Anyway,
Well, thank you.
thanks.
Just curious, since you just
Could make a
discussed
big
with Galileo and how it's been a balance.
Right.
Where does Giovanni Bruno fit into that?
Bruno was, again, an invention of the Italians in the 19th century. If you read Bruno's writings, the reason he was burned at the stake had nothing to do with his astronomy.
I thought it had been going on Europe, basically adopting every religion in every town.
Well, that, and pissing off everybody in both Protestant and Catholic Europe. And basically he was crazy. He was not the kind of person, I mean, the idea